Students, we have come to the last part of this module, battened columns. Here you can see the battenings here. So all these are called the battenings or battens. So usually battens are the plates or any other type of rolled sections used to connect the main component of compression members. The batten should be placed opposite to each other on the two parallel faces of compression members and should be equally spaced throughout the column length as shown in these figures. So the spacing should be uniform throughout the length of the columns. If you consider a column also, throughout the length of the column, the battening should be placed equally. Usually the battens provided at end of the columns are called as end battens or tie plates. The battened columns have the same strength as laced columns, but they are usually uneconomical and that is why they are used very rarely. Further, the battens are not recommended for a column usually subjected to eccentric load in the plane of connecting system. Now let us see the design requirements for battening as per IS 800-2007, clause number 7.6, page number 51. According to the clause, the number of batten should be such that the member is divided into not less than 3 bays. So this is a battening. So the member should not be divided less than 3 bays. And these are the forces acting here. The Vt divided by 2n, where the force is acting in the horizontal direction here, and the battens shall be designed to resist the simultaneous forces like this. Usually it is designed to take up the longitudinal shear force, then the transverse shear force which is called as Vt, and also a moment which is developed because of the development of Vt. So this moment is usually developed because of the Vt, and this Vp is also developed because of Vt. The formula is Vt into C divided by N into S, whereas the moment is because of Vt into C. C is this distance divided by 2N. We will see that when we take up the code provisions. Yeah, here we have the longitudinal shear which is given by Vb equal to Vt into C divided by N into S, and moment M equal to Vt into C divided by 2N, where Vt is a transverse shear force, C is the distance between center to center of battens longitudinally, N is the number of parallel planes, usually it is taken as 2, then S is the minimum transverse distance between centroid of the bolt group or weld, and M is the moment arising because of the transverse shear Vt. The clause 7.7.1.4 says the slenderness ratio KL divided by RE, that means effective slenderness ratio for batten column shall be taken as 1.1 times the KL divided by KL divided by RO, the maximum actual slenderness ratio of the column, to account the shear deformation effect. For lacings we have taken 5% extra. Here for battening you have to take 10% of extra slenderness ratio as the effective slenderness ratio. The spacing between the battens. Here, the maximum spacing of the battens C should be such that the minimum slenderness ratio of the component member C divided by Ry or C divided by R minimum shall not be greater than 50 or zero point 0.7 times the slenderness ratio of the member as a whole about the axis parallel to the battens, whichever is smaller. So these two values you need to remember. If you refer to the clause, you will get all these values. Now coming to the thickness of the battens. The thickness of battens should not be less than 1 by 50th of distance between the innermost connecting lines of the bolts or welds perpendicular to the main member. So T should be greater than LB divided by 50, where LB is nothing but S dash plus 2G, where G is a gauge distance, where G is nothing but the gauge distance. S dash is nothing but the two channels are usually placed back to back. That distance is called S dash. Further, the effective depth of the batten DE. The effective depth of the end batten should not be less than the distance between center of gravity of component member and should be more than twice the width of the component member. This one. The depth of intermediate batten is to be taken as 3/4 of effective depth of the end batten and should be more than twice the width of one component member. Hope it is clear. That means effective depth of end batten D dash or DE is equal to S dash plus 2 CYY, whereas the overall depth of end batten can be taken as D equal to D dash plus 2 into edge distance, or which is also called as the end distance. Now the transverse shear. The batten shall be designed to carry a bending moment and shear forces arising from transverse shear Vt should be equal to 2.5 times of total axial force on the whole compression member, similar to the lacing design. The overlap, if you are going for a welded connection, then coming to the overlap, for welded connection, the overlap shall be not less than 4 times thickness of the battens. It should be noted that the batten columns have least resistance to shear when compared with the columns with the lacings. So you have to be very careful about this. The bending moment we can calculate by using m by z equation, where z is nothing but td square divided by 6. So the equation to calculate the bending stress in this particular but design will be equal to 6m divided by td square, which should be less than fy divided by gamma m naught. And also we need to calculate the shear stress developed in the end batten and also in the intermediate batten, that is vb divided by a1, where a1 is nothing but the cross sectional area of the batten shall be less than fy divided by root 3 into gamma m naught, where fy is the yield strength and gamma m naught is the partial safety factor, which is usually taken as 1.1. So these are few of the code provisions we have to consider in the design of patterns. You can refer always clause number 7.6, page number 51 for more information. Thanks for watching. In the coming video lecture, we will take a problem of design of patterns. Thank you.